Hello everybody, welcome to Data Structures and Algorithms for Coding Interviews. I am your instructor, Nick White, and this is my first course ever. If you didn't see my YouTube video, I decided to make this course because a lot of people studied using my videos to get into companies, and they really enjoyed my teaching style. And people request me to teach on YouTube all the time. However, I moved towards making more entertaining style content. So this platform and the amount that you paid to have access to this platform and this course, this is where I'm going to be teaching from now on. Now, here's what you can expect. I am going to go over all of the fundamentals. That will be the first thing available through this course. So each data structure, I'm going to do an overview of the data structure, talk about how they work. I'm going to talk about time and space complexity, and I'm going to talk about famous and general algorithm techniques. Now, as far as timelines for this, I'm just going to continuously add content to the platform. So it's not all going to be available at once. I'm just going to continue working on it day by day and adding more things. Now, what you should not expect from this course is to automatically get into a FANG company. This should not be your go-to resource to getting into FANG. I'm not advertising it as that. I'm advertising it as me teaching what I know on this platform for people that like my teaching style. This is my teaching for the people that like how I teach. This is going to be on this platform. You can't expect this to be as good as all these other resources that have been around for years anyway, because it's only been a little bit over a month for me to get this basic content out, and I'm going to be adding stuff over time and improving it. Some videos might be removed and redone as I have more time to make things better. So with all that being said, I hope that you can go lesson by lesson. It should be in chronological order. Watch the videos. I want to make these just easy for people to understand, and for the people that can't solve like LeetCode and HackerRank questions on their own to study for interviews on their own. I hope that by the end of this, you will have found some value, and you can just go to those platforms and you'll understand how to start these questions and how to just continue and study on your own. As opposed to other courses, I want to make this a little bit entertaining. I think that's the point of education, is to be engaging. It's not all about the information, because if you're bored, you don't retain. So I'm gonna maybe put some jokes. I don't. If you don't like that, I'm sorry, but I think that's how I'm gonna innovate on the education system here. We're gonna add jokes. We're gonna add editing. We're gonna try and make this as good of a time as possible. So that is it for now. Welcome. Hope you find value, and let's begin. There are both conventional and unconventional ways to learn how to code, but I don't think anybody would recommend to learn data structures and algorithms before you know a programming language. And that's why before we get started, you should know at least one programming language pretty well. Now you might be asking, what programming language? A lot of people recommend using languages like Python or JavaScript because they have really easy syntax. My personal favorite language is Java. And this is just because to code out the data structures, you write the actual name of the data structure. To declare a hash map in Java, you write the word hash map. To declare a stack, you write the word stack. Whereas in Python and JavaScript, you might use brackets to represent an array, or curly braces to represent a hash map. It just gets a little bit confusing for me, so that's why I like Java. However, I will admit Java syntax is a little bit more complicated. But if you're already comfortable with the programming language, you should just stick with that. It doesn't really matter because I'm going to try to make this course as language agnostic as possible. And then you might ask, well, how well do you have to know a programming language? To answer this question, you don't need to be an expert. You just need to know core concepts. Things like basic syntax, variables, data types. You should know what loops are and how to loop through things, how to do for loops, while loops. You should know what an array is, and you should know about functions. Anything beyond that is a little bit advanced and programming language specific. If you need to brush up on your programming skills, I'm going to recommend some resources for you. To learn a programming language thoroughly, the two best resources in my opinion are The New Boston on YouTube, who has a video tutorial series for almost every programming language. He's entertaining, and it's a very smooth process to learn from his videos. If you're not a big fan of video tutorials, on the other hand, you can check out Code Academy. This is where I first learned to code, and it has interactive lessons to teach you a programming language step by step. But those resources take some time, and they go pretty in depth when they're teaching you the programming languages. If you're just looking to brush up on a programming language, I'd recommend websites like W3 Schools or Tutorials Point. You can kind of just skim through the sections and look for things you need to remember. And then last but not least, to make sure I'm comfortable with a programming language, I always go to HackerRank. Over the last 8 years, I've worked with around a dozen programming languages, and sometimes it's been a while since I used one. So I always head over to HackerRank, click the programming language I need to get comfortable with again, and solve some of the problems. They rank the problems from easy to medium to hard, and by the end of it, you'll be very solid with the programming language of your choice. Now, there's no need to stress out about all of this. You don't need to look at all the resources or complete everything I just said. I just need you to be able to do basic things like loop through an array. It would be nice if you knew the shorthand to add values to a variable. You don't need to master it. You just need to be comfortable. So that's it for before we get started. Go brush up on your programming skills, and I'll see you in the next lesson. All of these courses assume that you guys know what algorithms and data structures are already. But I remember when I was in college, before I had to take these classes, I had to take data structures and algorithms, 2 separate classes, 2 different semesters. I thought of them as if they were going to be like the hardest classes ever. I thought of algorithms specifically as being like this genius kind of mathematical programming kind of creative programming math kind of thing. And that's because the media makes it seem that way. In The Social Network, when they're talking about algorithms, they're doing like the face mash algorithm, and they write on the window like this clever code, and they're talking with the music, and they make it seem like they're super smart. And in the show Silicon Valley, they're talking about the compression algorithm that compresses 90% faster, and then they're gonna start a whole startup around this compression algorithm. But don't overthink this stuff, right? Like, that's the whole point of this course is, dumb this stuff down. Don't put this stuff on a pedestal. An algorithm is basically just a way of doing something. Like, if you have a task at hand, it's just a way of solving a problem. And you can solve problems in different ways, right? It's just one way to do something. Here's what an algorithm is, right? You have to get from your house to school. So think of an algorithm as whatever way you want to get to school. One algorithm is taking a car. One algorithm is taking a bus. One algorithm is walking. Now, the most efficient algorithm to get to school is to take the car. The least efficient is walking, unless the school is like right next to you. But you know what I mean? Like, it's literally just a way to do something. That's it. It's a way to do something, a way to solve a problem. You get problems in code, and you have to solve them in a certain way. And whatever way you do that is your algorithm. Okay, so let's look at a coding example. Pretty straightforward, pretty easy. Print the elements of an array. Now, there's a bunch of algorithms to do this. You could print the array from front to back. You can just loop through, print every element. That's an algorithm. You're just looping through and printing every element. Another algorithm is loop backwards through the array. Print them all in reverse order. Another algorithm is to go through it once. So you loop through it once and start at the first element and then print every other element. And then you could go through it again and skip the first element, start at the second one, and print every other element again. And it will print them all. Now, the third one is kind of just dumb, right? Why would you do that? There's no point of doing that. You would want to do it the more efficient way, the easiest way, is you just loop through and you print all the elements. So that's basically an algorithm. Think of that. You get problems, you solve the problem. The way you solve the problem is an algorithm, and some algorithms are good and some are bad. And in this course, the point is to figure out which ones are good, and then we want to find the best one. So that's about it for algorithms. Hopefully you guys understand. This is like, I don't know, I'm trying to make that as easy as possible to understand. Hopefully you guys get it. Now, data structures aren't all that different either. Data structures, that word's big, right? Scary, right? This might sound stupid, but literally, data structures are just a structure for your data. So you've probably worked with data before, right? We have numbers, strings, Booleans. This is all data, right? Literally an array of numbers, that's data. But while you might not be all that familiar with this stuff, you've probably only used an array before. Maybe you've used a hash map, or in Python, a dictionary. But these aren't the only ways that you can hold data. These are just structures for data that make sense in the scenarios you're using them in. Yeah, if you just have a bunch of numbers, or if you just have a bunch of strings, sure, you could use an array. But let's say you have a lot of data. For example, you have people. So you want to associate their name with all of this stuff about them, right? Their age, their gender, their height, their weight. You would not want to use an array for that. That doesn't make any sense. So an array would be a bad structure for that data. So yeah, an array is literally just a structure for data, and there's a whole bunch of other data structures that are used in specific scenarios to handle data in certain ways. And we're going to learn about a lot of those in this course. The main point of this video, which I think is important to put in a course for the people that don't get it, is do not be afraid of these words, because I used to be afraid of these words. Algorithms, data structures, you think of them as being these really complicated things, but really, an algorithm is just a way of doing something or accomplishing a task, and a data structure is just a structure for data. It's just a container for data. You want to use a different one depending on what you're doing at the time. We're going to go over all of that, but just so you guys know, this stuff isn't that hard. Might seem hard when you're first learning it, but it's not that hard, and eventually you'll get it. In the future, we're going to learn about these data structures, the different kinds, when to use them, and we're going to learn about algorithms and which ones are better than others and why. How do we measure which ones are better than others? So stay tuned. All right, guys, now it's time to cover some serious stuff. This video is about time and space complexity. This stuff is important because this is basically how you're going to measure how good an algorithm is. And when I say this is important, I mean it's the most important thing. If you don't understand this, then you won't be able to do anything after this. So it's really important that you guys understand this stuff. Okay? Got it? Okay, good. So time complexity is basically just how fast is our algorithm. And space complexity is how much memory does it use. And we basically want the code to run fast, and we want to use no memory. If you don't understand why we want our algorithms to go fast, well, I don't know what to tell you. I mean, it's pretty obvious. Do you want your program to loop through an array and have it take 5 years? No, you want it to be done instantly. We don't want to be sitting around waiting for programs to execute for no reason. Pretty obvious, we want our code to go fast, and memory-wise too, pretty obvious why we don't want to use memory. Like if I have a terabyte of memory on my laptop and I want to download Spotify or something, I don't want that to take up a terabyte of memory. I mean, just pretty obvious. So I obviously don't want my algorithm or little snippet of code to use up all my memory either. So we want our code to run fast, and we don't want it to use memory. Pretty straightforward. I really don't know what to tell you if you don't understand that. And I'm not trying to be hard on you guys. I just want you to understand that this stuff is intuitive. If you're not understanding this, you're probably overthinking things. Time, speed, space, memory. Time complexity are just 2 words in programming to talk about how fast an algorithm is. Space complexity are just 2 words in programming to talk about how much memory an algorithm uses. These are the 2 things we care about. How fast is it? How much memory does it use? Because think about it. In the real world, if you're given a job to write a program that solves a problem within a week, and you can only use the server given to you, you have to write a program with a good enough time complexity so that it's fast enough to solve your problem within the week, and that it doesn't use more memory than you have available. So these are the 2 things we care about, and in the upcoming lessons, we're going to talk about how we can generally measure both of these. This is how we determine whether an algorithm is good. If it's fast and it doesn't use a lot of space, that's a good algorithm. If it's slow and it uses a lot of space, that's a bad algorithm. All right, it's time for me to make the hardest video of this course and the most important video for you to understand so that you know what the fuck is going on. Now, I've actually explained big O notation, time complexity, space complexity, dozens of times. I could sit here and I could just tell you all this stuff, but I'm going to try and take an approach that isn't out there. Remember, this is how we know what a good algorithm is and what a bad algorithm is. And conceptually, this is probably the hardest thing that you need to understand and grasp about algorithms and data structures in general. You get this and you're pretty much good to go. You can kind of pick up everything else. It's all programming, but this is kind of like conceptually mathy kind of things to measure how good our algorithm actually is. So without further ado, let's begin. Now, the first thing I want you guys to do is to think back in that brain of yours, back to elementary school about math. Have you ever used graphs? You know, the x-axis, the y-axis, you could like plot things on the graph like this. This is a graph. Well, then you might remember that you can plot functions. You know, like y equals mx plus b, like the slope, the y-intercept, all of that crap. But yeah, like if you know you could plot things on a graph, like you can look up like graph my equation. So this is a graph and I can just enter equations in the top left and they will show up. So I wrote y equals x, which is linear because as y goes up, x also goes up. You can clearly see that when y is 1, x is 1. When y is 2, x is 2. When y is 3, x is 3. That's because y equals x. Here's another equation I entered, y equals x squared. And if you check, y does equal x squared. When y is 1, x is 1, because 1 squared is 1. When y is 4, x is 2, because 2 squared is 4. So y equals x squared. So 3 squared would be 9. So you could see when y is 9, x is 3. And then you could go to 16 for 4 squared, and you could keep going up and checking. This equation is y equals x to the x. When y is 1, x is 0. And that's because 0 to the 0 is 0. But also when y is 1, x is 1, because 1 to the 1 is 1. Now 2 to the 2, or 2 squared, is 4. So when y is 4, x is 2, because 2 to the 2 is 4. Now 3 to the 3 is not 9. 3 to the 3 is 27. So y should be 27 when x is 3. And if we go up and we find 27, you can see right down here it says 3. We go up and yeah, that's exactly what it is. Now when you're graphing things, you're usually graphing them for a reason. You graph these equations that represent something in math, and you would label the x-axis and the y-axis. You don't just graph things for no reason. For example, the area of a square. Maybe you would say the y-axis is the area and the x-axis is the length of one side of the square. But you can graph a million things, and you can have an equation for almost everything they teach you in math. Well, guess what? We can basically have these equations for our algorithms to measure the speed of them. So that brings us to big O notation, which is basically just simple math equations. Now, big O notation is basically just another way of writing a function. So in math, we would write like f of x or all of that crap, if you remember. Now, the big O is just the way to represent our algorithm's time and space complexity, like our speed of an algorithm or space we're using. The O is f, and the n is x. So just imagine that big O notation is just a way to measure the speed of an algorithm. So we can imagine our algorithm's speed as a graph. So if you were to graph our algorithm's speed, you would have the y-axis be the time that it takes for the algorithm to run, and the x-axis would be the amount of data that we're given. So let's look at it like this. Let's say we're looping through an array, and it takes 1 second for each iteration of the loop. So each element we look at, it's going to take 1 second each. And obviously that's not how long it takes. I'm just trying to get this into your head. But let's just say it takes 1 second per each loop through an array. Well, if there's one element in the array, that would take 1 second to loop through. If there's 2 elements in the array, that would take 2 seconds to loop through it. If there's 3 elements in the array, that would take 3 seconds to loop through it. And because the time it takes to execute the algorithm will go up proportionately with the number of elements in the array, the amount of data we have, this is a linear time complexity algorithm. So just like y equals x, where y goes up at the same rate as x, well, if we label the y-axis time and the x-axis the amount of data we have, then y will go up at the same rate x goes up. Time will go up as the data set grows. So it's a linear time algorithm, which we represent in big O notation as O of n. So instead of f of x or y equals x, we just write O of n. Now in big O notation, the n is actually just a variable. So you're going to write a big O notation representation of how many operations it takes your code relative to the data size. So like we went over in the loop example, if a loop is an operation and it's one loop a second, then it's a linear time complexity algorithm, and you would write big O of n time, and then you basically have to say where n is the size of the input array. Now that's just the standard way everybody does it, the like convention, but you could essentially write O of y or O of x as long as you say where x is the number of elements in the input array. But yeah, it's kind of just like a mini math function that represents your algorithm. Now I realize this is a lot to take in. I definitely struggled with this for a while when I first learned it, but it's really not that difficult. But I'm obviously saying that after knowing it, but I kind of felt dumb once I realized how simple it is. So in the next video, we're going to go over some examples of algorithms and their time complexities, and we'll talk about what good time complexities are and what bad time complexities are. All right, so I spent a decent amount of time trying to make concise edited videos about time and space complexity, you know, with little pop-ups and pictures and, you know, just trying to make it really nice and easy to watch. However, I can understand that some people maybe still don't even get it because it is kind of hard to understand at first. So I'm also going to attach this video to the course that I filmed over a year ago. This was a video I made all about time and space complexity and big O notation. Completely raw and unedited. It's a little bit over 20 minutes, but I figure if you don't understand yet, if you watch this whole video now, I would really hope that you would understand, because at that point, I think I did a pretty good job of explaining it after like all of this stuff. And no, this is not currently on my YouTube channel. It was up for a period of time, but was taken down because trying to do entertainment. But for however long it was up, it got 1,000 likes and only 16 dislikes, and all the comments were really positive. So I feel like with the edited videos, this is going to be some repetitive information, but maybe if you're missing something or you don't fully understand, watch this through. And then I really think that you should kind of get it at this point. All right, what up, programmers, coding people, YouTube? This video is going to be going over time complexity, a little bit of space complexity, some big O notation. I want to drill these concepts into your mind. I actually haven't made a video on this yet, surprisingly. So I want to get people to understand this stuff. Why do we even care about it? I guess we'll start there. But I do want to say I'm making this video because I think a lot of the videos out there, which there are some good ones, but people dive too into detail. So I am going to dive into detail. I should give you examples and stuff, but sometimes a tutorial or explanation can get ruined by trying to say every sentence right, so you don't get any criticism at all in the comments. But I am not going to, I want to make this more understandable. I'm going to explain this. For example, in this tutorial right here, where I'm going to tell you about time and space complexity, I'm going to pretend that one loop is a second. Like it takes a second to loop through each element of an array, because I think that's easier to understand. Whereas, some people might try and more accurately, precisely measure that. I'm not going to do that because it's way more easy to understand if we just think of a loop as a second when we're talking about time and space complexity. So why do we care about time and space complexity? First of all, if you are interviewing at any of the top companies, a lot of the standard interview process at probably half or more of the companies that you're going to be interviewing at, you're going to have to write some kind of algorithm or program that solves something, and you're going to be asked to explain the time and space complexity. And why? Why is this important? Why is this even in interviews? Well, a program when we're programming, we want it to be fast. If you're a software engineer and you're given a list of 20 elements, you can see this array right here, 1 through 20, and your boss says, hey, today's task, you got to go print every element of that array. Can you do that? And you write an algorithm that says, sure, boss, it's just going to take 3 days. He's going to be like, 3 days, dude, like you could loop through that. Like that should be instant, So that's this is a better algorithm, just looping through the array and printing each number. That's very, very quick. compared to, you could potentially write an algorithm that takes a really long time. So you want the program to be fast for obvious reasons. You want things to be done fast. Memory-wise, you want to use as little memory as possible. It's kind of just obvious stuff. You don't want to use memory, and you want the things to run fast. When we want to we write programs to automate, we write programs to do things. We want those things done fast. When would we want them done slow? That literally is never the case. And we don't want to use memory because that's resources, right? So we don't want to use time and resources. Want them as low as possible. Okay, we get it. We get it, Nick. We get it. All right, so we understand why time is important and space is important, but when we write a program and like our boss asks us, or the interviewer asks us, how fast does our program run? Like if we have an array of 20 numbers here and we want to print every number in the array, when they ask us how much time and space does it use, we're just doing a for loop here. We're not going to say, oh, this executes in 20 seconds and uses 1.2 megabytes of memory for the counter. No, we're not doing that. What we use is this thing called big O notation, which you might have heard before. And if you haven't, well then good, because this is a good spot to hear from. You can get confused when people talk about upper and lower bounds and big omega and all that crap. Forget about any of that. What it really is just O and then a variable. And this variable is key here. We usually use n. So usually you're going to say O of n squared, O of n log n, O of log n. But n represents, what n represents is anything. Usually it is the data size, or the whatever you're using for data. So if we're given an array here, in this case, n would be the number of elements in this array, but n is anything. N could be the number of nodes in a binary tree, n could be the number of nodes in a linked list, n could be the number of characters in a string, n could be the number of elements in the array. N could be anything. You have to say what n is. So when they say, what is the speed? What is the time complexity of the algorithm that you wrote to print every element of the array? And I'm doing a for loop. I loop through every single element. You can see here, if we had an array of size 20, it would go 1, 2, 3, 4, 5, 6, and it would print every single one of those numbers. In a for loop, it looks at every single number. So I'm going to say my program here runs in O of n time complexity. And I'm going to tell them, the interviewer or my boss or whoever, where n is the number of elements in my array that I'm using, or the input array or whatever. I get to choose what n is. I'm going to tell them what n is. So if I'm looping through an array, I'm going to say n is the number of elements in the array. And this is referred to as a linear time complexity, where you look through every element of the array, because as you add elements to the data that you're looking at, the time goes up in a linear fashion, exactly at the same pace. So if we have an array of size 1, since our algorithm is just looping through all the elements, it's looping through one element. And if it's 1 second per loop, that's 1 second to execute. If it's 5 elements, 5 seconds to execute. 10 elements, 10 seconds to execute. 20 elements, 20 seconds. So as you add elements, 21 seconds, 21 elements, 21 seconds to execute. It's directly proportional. As the data gets bigger, the time complexity grows at the exact same rate. And that's why it's linear. As time goes up, as data goes up, so does time. So that is kind of the idea of big O notation, is you get to pick what the variable represents, but also it's in relation. We're talking about the relationship between time and data. So how does the time grow as the data set gets bigger? Okay, cool. Now, there's many different time complexities. So this article is great. These are the most common ones. This is basically all you're ever going to look at in your career. There is constant time. Constant time is just some kind of calculation. There's no data size we're dealing with or data that we're dealing with. It's just like 5 plus 5, for example. If in your algorithm, for some reason, we wanted to print 5 plus 5 in the loop, that is a constant time thing. That doesn't go up. There's no extra time as the data scales. There's no change in that value. It is constant time complexity. Another common one is log of n. We'll get into that in a second. Linear, we just went over, n log n, n squared, 2 to the n, and O of n factorial. This article I'm linking in the description. Read through this article, but these are the main time complexities you'll ever have to deal with. You could see they labeled it here perfectly for us. Horrible. These are bad time complexity. That means they take a really long time. And then these are better time complexities down here. They put linear and fair. They put these ones at the best. Okay. Now, let's get into n squared, the next most essential time complexity and common time complexity that you guys need to understand. Okay. All right. So for an example here, here's an algorithm that is n squared where we're printing elements. And we're printing 1, for example. And let's say we're doing this on 1, 2, 3, 4, 5. We print 1. You see this outer loop here. We print 1. Now, once we print 1, we print every element in the array. So our output is 1, and then we go through the whole array. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then we print 2, because it moves on to the next iteration of the outer loop. And then we print 1, 2, 3, 4, 5. And then we go to 3, and then we print 1, 2, 3, 4, 5. So you could see how this is n squared, because for those n iterations where we saw an outer loop, this one simple for loop that's just 1, 2, 3, 4, 5. If n is the length of the input array, well then that is O of n. This is O of n, but 1, and then times O of n, because we're doing that O of n within an O of n. So nested loops, most of the time, they are n squared. However, don't always take that for what it is. You have to look through what you're looping through, right? On our outer loop, we're looping through the input array, and on our inner loop, we're also looping through the input array. So if n is the elements in the array, yes, that's O of n squared. But let's say we have 2 arrays. One of them is 1, 2, 3, 4, 5, and then one of them is just 1 and 2. If we're looping through, and this one is called array 2, and then this one's called array 1. If this is looping through array 1 and this is looping through array 2, these are looping through different things. So if n, when you tell them the time complexity is the number of elements in this array, this is not an O of n squared algorithm, because this is not doing O of n times O of n. This is doing O of n times a different variable if it's looping through this array. So you would say something like O of n times m. So you'd make a new variable. You'd say where n is the number of elements in this array and m is the number of elements in this array. So it's n times m. And that should really solidify what this n squared thing is, how these algorithms are kind of working. I really hope it does. Okay, so let's recap what we learned so far. O of n is where we have the time going up in a linear fashion with the data. As an element gets added to the data set, a second gets added to the time. O of n squared, however, is n, it's taking the number of elements and squaring that to get the time. You could see one element is 1 second, but as the data goes up, there is that steep curve right there. You could see 1, 2 elements is 4 seconds. 3 elements takes 9 seconds, because if n is 3, n squared, 3 times 3 squared is 9. 4 elements is 16. 5 elements is 25. Look how fast this is increasing, the seconds. So this is a slow algorithm. We deal with huge data sets when we're actual software engineers. So if you're dealing with a data set of 10,000 elements, or if you're dealing with a data set of 1,000,000 elements, well, then an n squared algorithm is going to be 1,000,000 seconds times 1,000,000 seconds, and that could be forever. So that's why we want to reduce this algorithm. Now, one thing that is an n squared algorithm is calculating the frequency of elements in an array. And by frequency, I mean if we have an array and we're given the task to, let's say we call this frequencies. Let's say we have this array and we're told, hey, find out how many of each element there are in this array. Find out how many 1s there are, how many 2s there are, how many 3s there are, how many 4s there are in this array. And we could see right here, there's 1 1, 2 2s, 2 3s, and 5 4s, I think. And we want to figure that out. Well, you could do an n squared algorithm, right? Right here. You loop through each element, then you loop through the whole array and see how many of those elements in the outer loop are there. You have a counter, and there you go. N squared, right? A nested loop, right? We can reduce this. We could totally reduce this, which is awesome, if we just look at this. Look at this. This is now O of n, where we're just looping through every element of the array once. But what are we using here? Well, we're using external memory. You can literally use memory, and this is very, very common in algorithms and data structures and time, space, all these interview questions. You use a data structure, a structure for data, and you store results, or you store some pieces of data to speed up the performance of your algorithm. We don't always want to do this because we might not have the memory, but if we have the memory and we know that, and our algorithm is super slow right now, like n squared is slow, right? We can get it to O of n by just using a hash map or a dictionary, for example. So we have this dictionary, right? And we can just keep track of the count. We could put elements into the dictionary. So we see a 1. Oh, we see our first 1. Let's put that in there, right? We put it in the storage. And then we see our first 2. Okay, put that in with 1. Oh, we see 2 again. 2's already in there. So let's increment the count. Oh, we see our first 3. Let's put it in there with its initial count. Oh, we see another 3. Let's increment the count. Oh, we see a 4. And this is just looping through the array and incrementing the counts inside of a data structure. So instead of doing that n squared loop, which is really slow time complexity, bring our time complexity down by using data. So you have to think about these trade-offs when you're writing programs, how much memory you have, how much time you want to use. And in an interview, think about this stuff. Now, and cube, for example, would be looping 3 nested loops through the array, right? So as you nest loops, just remember that you want to look at what you're actually looping through, because it doesn't always necessarily mean n cubed if these are different arrays. So we remember that. And you can make up more variables as you go. If it's array 1, if these are all different arrays, then you could say the time complexity is O of n times O of m times O of what element O? Do I know my alphabet? Wait, O of n times, we could say O of L. All right, I guess it was going backwards, right? I thought it was going forward. Okay. That makes me untrustworthy not knowing the alphabet. All right, dude, I'm stupid. But all right, so we understand what O of n is. We understand n squared, n cubed, constant time. We know we can reduce our time by using memory. What about O of log of n? What does that even mean? Logarithms. I haven't heard that since whenever, algebra or whenever you learned that. Well, logarithmic algorithm is really good. Log of n is really good. And this is a pretty rare time complexity. You're going to see it in a few things, but binary search being probably the most popular, where if we have a sorted array, so if we have 20 elements, you can see it's sorted, meaning 1, 2, 3, 4. It's sorted in increasing order. And let's say we're told to find the number 15. Well, if we don't know what's in the array, what we could do is we could loop through the array. And we could say, okay, if we found the element, if the current element we're looking at is equal to 15, we found it, and we'll return the index. So that takes 15 loops, 15 seconds to get to 15 if we're doing just a loop through the array. That's a long time. So now what binary search does is it says, okay, let's look at the middle of the array, right? We know the length of the array. The length is 20. So we'll take the length, divide by 2. 20 divided by 2, 10. And look at that. We're at the middle of the array. And we're going to say, hey, is what we're looking for greater or less than what the middle of the array? So at the middle of the array, we have 10. 15 is greater. Since it's sorted, and binary search only works on sorted arrays, we know it's on the right side. We know it can't, how could 15 be before on the left side of 10 if it's sorted? It's all less than 10, so 15 is not less than 10. So it's logarithmic is when you're eliminating half of the search space. So like binary search, we're eliminating that. Screw it. It doesn't even matter. We'll never iterate over any of those values. We know it's not there. And then you look at the middle of the new search space and boom, 2 iterations. It took 2 seconds to get to 15. And if we did it in the linear loop, it would have taken 15 seconds. Now, This is extremely good algorithm for huge data sets. For example, the main example is if you have a phone book with 2,000 pages, massive phone book, however many pages there are, and you're looking up someone's name, if their last name starts with an S, you're not going to go page by page till you get to S. You're just going to flip halfway, say, oh, I'm at M. S is clearly on the right side of the book. Flip halfway again until you get to S. That's literally a binary search. It's a sorted book of names. So logarithmic is eliminating half the search space. Now the opposite of logarithmic would be exponential, like 2 to the n. So this is really bad. Logarithmic, really good because it's super fast. 2 to the n, really bad. Now in this article, they give a really good explanation. Algorithm is said to have exponential time complexity when the growth doubles with each addition to the input data set. And the growth does double, and there's just so much repetition in the Fibonacci. Like, you could look here at all of these repetitive calculations. Like, if you look, see 4, look at this tree structure. This 4 tree structure is right here. This 4 tree structure is right here. And what you'll learn eventually is that you could use data like dynamic programming to store, like the first time you do the calculation for 4, store it in a data structure. So if you do it over here, and then you'll have it for when you calculate it over here. So like there's a lot of things with really bad time complexities. O of n factorial rarely comes up, but there's a lot of really bad time complexities. We want to get down to really good time complexities. I don't think I want to confuse you with a lot of, the higher level ones. The main ones you're going to deal with, we already went over. N log n is one we didn't go over, which is like sorting algorithms. The best sorting algorithms are merge sort, quick sort, heap sort. Those get to n log n. However, in certain scenarios, very specific scenarios, there are things like radix sort, bucket sort, counting sort, where you could get to linear sorting. But those are very, very like niche and specific cases. So the thing you need to understand is that there are upper bounds, there are there are best case scenarios, right? Printing every element of an array, you can't get that faster than O of n. I can't print every element of the array in constant time, for example. Like, you can't push it. You can improve algorithms, but you can't keep pushing it to the point where you can increase it. There's a certain point where like you're at the best possible one. So like the optimal solution is what you call that in a coding interview. And I hope I kind of made this clear for everyone. Like, space complexity is the same thing. If you have an input array that looks like 1, 2, 3, 4, 5, and then, maybe we use a stack in our approach and we keep track of these values and we put them into the stack. Well, if we use every value, if we're talking about O of n as the number of elements in the array, and then we use extra space like a stack where we put every n element in the array, we use O of n space. Now, if we kept track of a 2D array where we kept pushing the input array of size n onto this like main array as space, because we had to do some kind of calculations, that'd be O of n squared space. And you could kind of figure it's like the same thing for space complexity. I hope I kind of made it clear. The main things I want everyone to take away and focus on from this are O of n squared, knowing that every double for loop isn't O of n squared, knowing that you have to look what you're looping through, and just thinking about what the variables represent and kind of understanding that. That's like the main takeaway, not to confuse you with too much. Now, I will say this article, which I'm linking in the description, these were really helpful for me when I was getting into programming at first. These little charts right here, they show the time and space the time complexities of the data structures. So like there's a million data structures, of course, you might not know, but yeah, there's a bunch of data structures that we use to make algorithms faster, or we use in certain scenarios. And it shows you that these methods, they're like the data structures have methods that do things, right? When you use built-in methods, like a built-in sort, that takes time. A built-in index of, or last index, where you get the last index of an element in an array, that takes time. This isn't instant stuff that is just happening magically. Those have implementations behind the scenes in programming languages. So those take time. These data structures all have things like accessing an array. There's indices in an array, so you could access instantly. Boom. But in a linked list, for example, you can't do that. There's no indices. You have to loop through the array to get access to a node or a value. And deleting and inserting into an array shifts all of the values because the indices get messed up in the array. So that's O of n. That's like a whole shift. But For a singly linked list, it's constant, so you can just add things on and it's completely fine. So if you want to think about what kind of program you're writing. If you are inserting a lot and you need some kind of data structure to handle data, or you're inserting a ton, maybe use a singly linked list. If you're accessing a lot, maybe use an array, for example. But there's a ton of this stuff that you can look up. Binary tree, a lot of logarithmic stuff. So just a lot of stuff. Then it has like this chart down here just of the basic sorting algorithms where you look at, and yeah, there's like counting, sort, radix sort, and stuff like that. And yeah, really cool. That's kind of like my rundown. If I didn't get everything specifically right, I think it's fine, because I think I did a good job explaining it in a digestible way that is a little bit easier to understand than like having the specific every single detail right. So hopefully you guys understood. Let me know if you did. Let me know if you didn't, I guess. And if you didn't, that sucks, because this is a long video. Like and subscribe. Appreciate everyone that watches. And yeah, that's it. Join the Discord in my thing and follow me on Instagram and Twitter. All right. Hash maps and hash tables. These terms can be used interchangeably, even though there's slight differences between them. I generally like the term hash map, so I'm going to stick with that. Hash maps are one of the most common data structures that will come up in all of data structures algorithms. Any of the coding interviews that you might have, you're probably going to get a question that requires you to use a hash map. And that's just because they're so useful. Hash maps are a kind of data structure where you can associate a key and a value. It's the perfect data structure for associations of data, because like data is associated, right? Like if you wanted to keep track of test scores, for example, the key might be the student's name and the value might be their test score. And so a hash map would be like a data structure where you'd have all the students' names as the key and then all of the students' test scores as the values. And the best part about a hash map is you can look up a value by its key in constant time, which, as we know from the time complexity videos, is the best case scenario. So not only can we associate data, but we can store this data and then look it up later on by a key in a very short amount of time. So you can see how this could be very useful. Now, just on a side note, as far as coding interviews and algorithm questions go, you're going to come across a lot of questions where you come up with a pretty slow and crappy solution. In a lot of the cases for these problems, you can simply just use a hash map. Just think about how you can use a hash map in the problem, and it will speed up your algorithm substantially. And in a lot of cases, you'll find the optimal solution just by using a hash map. So for any coding interview you go into, you really should just have hash maps at the top of your mind. Now, there's a lot of complexities that go into hash maps or hash tables, but we do not really need to dive deep on that stuff. In any legitimate academic setting, like a college or something like that, where you're going to learn about data structures and algorithms, you're probably going to dive a little bit deeper into hash maps. I remember I took data structures and we dove pretty deep into hash maps, and it kind of confused me. So the actual way that a hash map works behind the scenes is not 100% important for your success in passing a coding interview. But just generally speaking, a hash map's behind the scenes implementation is actually using an array. So a hash map is like an array, and then there's a hashing function. That's where the hashing comes into play. And so you'll have these key value pairs in the hash map, and the key that you can look up will actually be passed through a hashing function, and using hashing, it will be turned into an index of the array, and it'll get mapped to an array index, and then, the hashing function, when you look it up again later, will map to the same index. You can look it up in the array. So behind the scenes, a hash map is really an array, and we just have a hashing function that maps keys to the array indices. And then there are more things you can go into, like collisions and blah, 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 but that's just going to confuse you. So there's no need to go into that right now. What's important is we understand how to use them. So let's look at a little bit of code. In languages like Python and JavaScript, using a hash map is going to be as easy as using curly braces. In Python, we have these things called dictionaries, but it's the same thing, key value pairs. You could access the keys by doing .keys. You could access the values by doing .values, or you can get a particular value just by using the name of your hash map .get and passing in the key of the value you want to get. It's also pretty straightforward to insert and remove values from your hash map. You can see at the bottom we're adding the key value pair of Jane and 004, and then we're removing the key value pair with the key of Dave. Now in a language more like Java, the syntax might be a little bit more complicated. However, when we declare our hash map, we use the actual word hash map. We also have to specifically declare what type the key and the value are. And then yeah, there's similar concepts like get and put, where you get values and put values into the hash map, and you can do things like check if a value is already in the hash map. But altogether, this stuff is pretty language specific, and you could just look this up on your own with your language of choice. I just wanted to show some sample code so we kind of understood how it works. In this video, we're going to go over a very famous data structures and algorithms problem, twosome. This is a cool problem because it helps showcase how a hash map can help us speed up the time complexity of our algorithms. So here's the problem. Given an array of numbers, like in this example, we have 3, 4, 2, 1, 9, 6. We need to find two numbers that add up to the target. So we would have like a function that takes in an array and a target value, and we need to look through the array, find two numbers that add up to the target. And then we want to return the indices of these values. Okay, so the only two values in this array that add up to 7, which is the target, are 3 and 4. 3 is at index 0, 4 is at index 1, so we would return those indices as our answer. By the way, we're going to be told that we can assume there's only one answer per input. So there's going to be exactly one answer for any input that we're given. Just so we're comfortable, let's look at one more example. So if we're given the array with the values 3, 4, 2, and the target is 6, we need to find two values that add to 6. So that's 4 and 2. 4 plus 2 is 6. And those values are at indices 1 and 2. So we return the indices 1 and 2. Okay, so now we have to write an algorithm or like implement a function that will take in this array, this target value, and it's going to return the indices of those values that add up to the target value no matter what the input is. So we need to come up with that algorithm. We need to make this function. We got to implement it. And well, how would we like go through an array and find two values that add up to the target? Well, if you think about it a little, it's not that difficult of a problem to solve. So since we're looking for two numbers that add to the target, we're obviously going to need to look at two values at a time. So a simple solution to this would be to loop through the array number by number, and then for each number in the loop, you would loop through the whole array again, excluding the current number you're at, and check if the values add up to equal the target. And if they do, you return their indices. So this is what the code for an approach like that would look like. You could see we have an outer loop looping through each number of the nums array, and then we have an inner loop that also goes through each number of the array. And as long as these loops aren't overlapping at the same number, we add the two different numbers together, see if it's equal to the target, and if it is, we found our pair, so we return the indices. And for those of you that are using Java or something more like Java, this is what it would look like. Same thing, you're looping through each number of the array in the outer loop, then you have an inner loop that loops through each number of the array. As long as they're looking at different numbers, you check if those numbers add up to equal the target, and if they do, you return their indices. So you might be thinking, boom, done, solved. But unfortunately, that's not how this works. In algorithms and data structures, we always want our solution to be optimal, and this solution is not optimal. It's actually the brute force approach. Brute force meaning we generate all possibilities because we're looking at all combinations of numbers, and then we find two that add to the target. And this algorithm is actually going to run in O of n squared time complexity. If we're saying n is equal to the number of elements in the array, and as we loop through each element, we loop through every single element, that's going to be n times n, which is n squared. And that's pretty slow in this case because we can actually improve the time complexity by using a hash map. So you might be thinking, well, how does a hash map help us? Well, one thing you might remember about a hash map is you can put things in and retrieve things from a hash map in constant time, meaning that time will not count towards our time complexity at all. So essentially what we could do is we could loop through our input array and figure out what other number we would need to add to the current number we're looking at to equal our target value. And as we loop through the array, we will just add each number with its index. So the key will be the current number and the value will be the index. And then in constant time, we can look into our hash map and see if that number is already in there with its respective index. If it's not, then we haven't seen that number before. And if we have, we can just retrieve it in constant time and we'll have its index ready to return. So here's what the Python code would look like for this approach. You would initialize your hash map and then you'd loop through the numbers array element by element. You would calculate the difference between the target and the current element you're looking at to see what number you would need. And if you've already seen that number, then you can just extract its index and return it along with the index of the current element, because that would be your pair. Otherwise, as you loop through the numbers, you're just going to be putting them into the hash map with their index, with the value as the key and the index as the value. And this is the code for the Java solution. If any of you guys like Java, we initialize our hash map, we loop through element by element, we calculate the other number we would need to add to get target, and if we've already seen that number, then in constant time we get its index and return that along with the current element's index, because that would be our pair. And if not, we're just going to add each element that we see into the hash map along with its index. So just from utilizing our hash map, we were able to eliminate one of those nested loops and get our time complexity to linear runtime, meaning that in the worst case, we're going to look at every element only once. And linear time complexity is a huge improvement compared to our n-squared time complexity that we previously had. Now, we did add some space complexity by using a hash map, but if we're concerned about time here, then you can see how important hash maps are because of their constant time operations. That is just one use case of the hash map that we just looked at to improve our algorithm. I hope you guys understood that. And yeah, that's it. Hash maps are dope. All right, let's talk about hash sets really quick. In my opinion, these are one of the easiest data structures to work with, so we don't need to spend too much time on them. So a hash set is kind of based off of a set, like in mathematics. A set in math is an unordered collection of objects with no duplicates allowed. So a hash set in programming is just going to be a set of data, and yeah, just like a collection of data, and you can't have duplicates. So whether it's integers, strings, etc., you just can't have duplicate values. And then the best part about hash sets, of course, is the time complexity of the operations. Just like in a hash map where we use hashing and we have those fast time complexity operations, same thing with hash sets, we use hashing and we get those constant time operations. Adding something to the hash set is constant time. Getting something from the hash set is constant time. Checking if something is in the hash set is constant time. So it's just a little container for data, and if you need to purge duplicates and some kind of problem, if you're going to be dealing with a lot of duplicates, you might just want to have hash set at the top of your mind. So let's say we have an array and we're able to modify it. When we add elements to our array, they're going to be added in order. And in addition to that, each element will have its own index. So we'll know exactly where each element is. The difference between arrays and hash sets is arrays have ordering and indices. Hash sets are unordered and have no indices and also no duplicates. That's pretty much it. This was what it might look like to implement a hash map behind the scenes. So the important things we need for our hash set is we need to be able to add things into the hash set or remove things from the hash set and check if things are in the hash set. So that's why we have the add, remove, and contains methods. Behind the scenes, just like how a hash map is implemented using an array and hashing, we have a hash set implemented using an array and hashing here. You really don't need to understand the hashing function at all to pass your coding interview. I'm basically just showing you so you kind of understand what it would look like. So it's basically implemented with an array, and then we have this hash function. We use this hash function in all our methods to map to the correct indices, and then the code for the methods is pretty basic besides that. Now in a coding interview, you're most likely not going to be asked to implement any data structure. You'll be asked to use them. And that's why most of the data structures are built into the programming languages for us to use. So in Python, you could just use a set, which would just be parentheses. In Java, you would just use the hash set class. And if you use any other programming language, just look up what it is on Google. In this video, we're going to go over a pretty basic problem. This problem's called isUnique. So here's the problem. You're going to be given an array of values, and if all of the values in the array are unique, you return true. If they're not, you return false. Basically, it's the opposite of contains duplicate, which is a problem listed for you to try out. So before we get started solving the problem, let's just look at a couple examples. So if we were given this array of data and we want to return true if it's unique, meaning all the values are distinct, meaning there's no duplicates in the array at all, we would return false. It is not unique. And that's because there are two number 3s in this array. In the next example, we would return true because all the values in this array are unique. So this array is unique. There's no duplicates in the array. And in this last example, we would return false because all the values are unique except for that last one. You could see there's a duplicate value 1, so false, not a unique array. So if we were just to solve this based on our intuition, what we really need to do is just find one duplicate value in the array. If we find a duplicate value, that means the array is not unique, so we're going to return false. And if we went through the whole array and we couldn't find a single duplicate value, that means it is unique and we'd return true. So an easy way to do this is to just have nested loops, where at the outer loop, we're just looking value by value through the array. And then in the inner loop, we also go value by value, just looking for a second occurrence of the value we're currently looking at in the outer loop. We'll have a simple Boolean variable called foundDuplicate, which is set to false originally. And if we ever find a duplicate, we'll just set it to true. And this is a pretty straightforward solution for us to come up with to solve this problem. However, the speed of our algorithm to solve this is not very good. We'll be looping through all values of the array for each value we look at in the outer loop of our solution. So that's the number of values in the array times the number of values in the array. So if we say n is the number of elements in our array, that's going to be an n squared time complexity. Now, using the awesome power of the hash set, which we just learned about, we can actually reduce our time complexity to linear. And as soon as we saw the word unique or duplicates, we should have been thinking of hash sets already. This is what the code would look like in Python and pretty much any other language. It's nested for loops looping through the array. We just have a simple Boolean variable foundDuplicate. Right, guys? The outer loop loops element by element. The inner loop loops element by element. Just looking for two of the same values. And if we find that, obviously the array is not unique, so we have to return false. And if we don't after those nested loops, well, then we can return true. If there's n elements in the array, that's n times n, which is n squared time. We do not, however, use a data structure, so it's constant space. Okay, so to improve our algorithm's time complexity, we can literally just use a hash set, go through the array element by element, adding values into the hash set, and then we just check at each element, hey, is this already in our hash set? And if it is, then we found a duplicate and the array is not unique, so we return false. And if we make it through the whole array and we don't see a duplicate, then it is unique and we return true. So it's perfect for a hash set to improve the time complexity. So the time complexity with the hash set is going to be linear, O of n. We just traverse through the whole array once in the worst case. And then we also have a space complexity here because we use a data structure, and that is going to be O of n space. This is what the code would look like in Python and pretty much any other language. You'd basically just initialize a hash set, loop through each number, and then put them in as you traverse through the elements of the array. And at each step in the traversal, you just want to check if you've already seen that number, and that's a constant time access from our hash set, so that doesn't really take up any time for us. So yeah, just traverse. Look if that value's in the hash map. If it is, we found a duplicate. If we make it through the whole thing and we don't see a duplicate, then we return true. One thing I've always loved about front-end programming is that as you code, with each line, you get to see visible results. Like, you get to see the user interface change in real time. But unfortunately, that's not how it works in back-end programming. However, if we were to code up a node class for a singly linked list, it would look something like this. Each node of the singly linked list would have a value as well as a next pointer to the next node in the singly linked list. And if this code were to render in some kind of user interface, it would look like this. This is usually how a linked list node is represented visually. As you can see, the node would contain some form of data and then also the address to the next node. So it will be pointing to another node, or null. And so this is just a node, but a singly linked list is made up of one or more nodes. This is what it would look like if there were multiple nodes. You could still see that each node will hold some data and a next pointer to the next node in the linked list. The first node in the linked list is often referred to as the head node, and the last node is often referred to as the tail node. So this is a commonly used data structure, but it's kind of confusing because it's very similar to an array in the sense that it's like a contiguous linear group of data where you can do similar things, like you can traverse a linked list just like you can traverse an array. However, there are some very distinct differences. Let's take a look at one of my favorite charts. This is called the data structures cheat sheet, and it's pretty much the best thing ever because, as you can see, it shows all the data structures, in addition to common operations that they have and the time complexity of those operations. So you can like directly compare what scenarios you would want to use a data structure over another one. So here's the big difference between linked lists and arrays. If you look at the array, you can see insertion and deletion into an array is a linear time operation. So if you're working with an array and you're allowed to modify it, like you could see dynamic array, if you were to insert or delete values, it's going to actually have to shift the indices of all the other values over, and that's why it's linear. Whereas in a linked list, whether you use singly or doubly linked lists, you can easily insert and delete nodes from the linked list. And that's just because you have to do some simple pointer reassignment. However, in linked lists, we could see they're better in insertion and deletions, but in an array, you can access values by their indices in constant time. So if you know where your value is in your array, you can easily access it instantly. But in a linked list, there are no indices. You would have to traverse until you find the value you're looking for. So while linked lists and arrays seem similar, those are the big differences in the operational time complexities. Okay, so we get a singly linked list. It's a linked list. The nodes point to the next node, right? It's just a collection of nodes. But what about a doubly linked list? Well, single means one. Double means two. So doubly linked list nodes have 2 pointers. Each node will point to its next node, so it'll have a next pointer to the next node, and it will also have a previous pointer, which will point to the previous node. And yeah, that's pretty much it. They're like the same thing other than that. One has 1 pointer, one has 2 pointers. This is what the code for a doubly linked list node would look like. Each node would have a value, just like in a singly linked list, as well as a next pointer. But in addition to that, there would also be a previous pointer to the previous node, and you could see that here. And then this would be the visual representation of that code. Just like in the code, you could see each node has data, a next pointer to the next node, and a previous pointer to the previous node. And this is what a doubly linked list with multiple nodes would look like. You could see each node with the previous and next pointers, and you could also see the label for the head node being the first node and the tail node being the last node. So to summarize, in this video we covered the 2 types of linked lists, singly and doubly, as well as the differences between a linked list and an array, where linked lists work better for insertion and deletion, and arrays work better for indexing, because they have indices and you could look up values in constant time at a particular index. So now that we generally understand what a linked list is, let's look at some problems. One thing I want to do throughout this course is give you guys insights into things I personally believe after interviewing, hundreds of times at real companies, because I apply to thousands of companies and I often interview for no reason, even if I don't want to work there. Other people don't do that, so they might not understand the perspectives I give, but here we go. This is one of them. As far as linked lists go, they are one of the easiest data structures to learn and master. The problems for them don't get that hard, technically. There's only a certain amount, and you could kind of learn it all pretty quickly. However, this should not be occupying a ton of your mental space. Like, you should not focus on this that much, because out of every single interview I've ever done, I've never been asked linked list problems. Doing all the problems, you could do them really quickly, so you might as well. But after that, you shouldn't keep going back to them and focusing and stressing out over them, because in the real interview, they do not come up that much. So our brains can only handle so much information, or at least mine can. And you like to keep fresh on the most important information. So this is, I would say, not the most important information. But with that being said, it is easy to learn. So let's just go over it really quick. Everybody knows that you can traverse and print the values of an array. And with a linked list, you can do the exact same thing. Since a linked list is a collection of nodes that point to each other, you can traverse node by node through the linked list and print the values of each node. And the code to do that's actually pretty simple and similar to how you would do it with an array. So now here's the difference with linked lists. In an array, you're going to have all that data stored in one variable. And you can use that one variable to do your traversals, to access elements, to modify the array. But with linked lists, not everything is stored in that one variable. Each node of the linked list is going to be its own individual object. So when we're given linked list questions or tasks, we're going to be given access to the head node of the linked list. And then you have to use the head node and its properties to get to the next node in the linked list. And if you remember, each node has a .next property that points to the next node. So this is completely fine. So to traverse a linked list, what you're going to do is you're going to make your own node variable. This is going to be kind of like a temporary object that we use just to latch on to each node and traverse the linked list. So you could call it temp, but oftentimes people call it current or current node. So you're basically going to make this node and then set it equal to the head node of a linked list. So now we have our own variable set equal to our head node. And basically now we can use that variable to do anything we want with the head node. So we can access its properties to print the value, or move on to the next node. And to move on to the next node, we're just going to reassign our variable that holds the head node to be equal to head.next. And since our variable currently is the head, we just have to do current node equals current node.next. And this is basically how you move from node to node in a linked list. So now instead of a for loop where we loop up to the length of the array, so what we could do is we could loop until the node is equal to null, because that's what the last node will point to. So the current node will just keep getting assigned to the next node in the linked list, and we'll keep printing the value as long as the current node is not equal to null. And once current node is equal to null, that means we've hit the end of the linked list. So here's what our code would do if we had this linked list. So the head would obviously be the node with the value 1, and that's what we'd be given to work with. So if we wanted to print the linked list, we would set current node equal to head. And then we just have a simple loop where we print each node's value and we go to the next node by saying current node equals current node dot next. And then the loop will finally end when current node is equal to null. And that means we're at the end of the linked list. All right, this is one of the linked list problems I'd love for you guys to check out. So given the head of a linked list, which is how it's going to be in every linked list problem, you're going to be given the head node of a linked list, insert a new node before the head. The next value in the new node should point to the head. So the .next property in our new node should point to the head, meaning it comes before the head node, right? We're just adding a node before the head, and the data should be replaced with the data that we're given. So this is exactly what it would look like. So let's say we have this linked list, and the head node points to the node with a value of 1, and we're given the data with the value 0. Then what we need to do is we need to create a new node, and the new node's value, the new node's .data property, needs to be equal to the data we're given. So it needs to be equal to 0. And the only other thing is we need to point its .next property to the current head node, which is the node of the value of 1. So now it becomes the head node. And then we just need to reassign head to the new node because that is obviously now the head of the linked list. And then we just return that node. So sometimes there's a lot of extra stuff in these questions that might actually confuse us, but let's just read through it all carefully. Complete the function in the editor below. We're going to get the parameters to the current head of the linked list, which we obviously need, and then the data for our new node. And then we have this input format section, which might confuse us a little bit because it says the number of elements to be inserted at the head. Because HackerRank does this thing, it's kind of similar to competitive programming where they have their test cases and they have this like loop function here. But basically they have everything set up where they're reading in all of the data and they're going to run all these test cases. For the function, we just have to do what the function wants us to do. So we're just adding one node to the head, and then they're having a bunch of test cases run down here. So don't worry about any of this stuff. So if we head over to our editor, we could see our linked list node structure. So we have the data property and the next property. Like we said, we want to point next to the head, and we want to set data to whatever data they give us. So we could just easily initialize our new node by saying new node is equal to new singular linked list node, and we could pass the data into it. Then all we need to do is set new node.next equal to our head node that we're given. So the new node points to the head. Perfect. And then we just want to reassign our head equal to new node, because new node will become the head node because now it's the first node in the linked list. And then we can return the new head of our linked list, and we should be good to go. It's as simple as that. 4 lines of code, guys. It's not that difficult. You create a new node, pass the data in, point the new node at the head, update the head, return the head, right? Hopefully we all get that. And yeah, we should be good to go. So if you're curious about the time complexity it takes to add a node to the end or beginning of a linked list, it's actually constant time, and this is perfect to demonstrate what linked lists are good at. They're perfect for adding things to the end and the beginning because it's so effortless and doesn't take much time at all. And then for those of you that use Python, it's exactly the same thing. You just say no node equals singularly linked list node, and then we pass in our data. Sorry, I messed up a little bit there. No semicolons Python. New node dot next is equal to list. So we point it at the head, and then we can honestly just return new node, guys, because it already is the head by default. But we could also say list is equal to new node and return list, or we could return new node. It doesn't really matter. It's head either way. But yeah, that is it. We're good to go. Let's not overcomplicate this. Stacks are stacks. Like, do you know what a stack is? Like, you stack things. You ever see cup stacking? They made me do cup stacking in gym class when I was growing up. And that's how I learned what a stack is. You stack things on top of each other. Now, in programming, stacks are only confusing because they're implemented in so many different ways. But honestly, you can just use something as simple as an array or a list to implement a stack. All it is it's just a way to structure data in which each piece of data goes on top of the last piece. And when you want to remove data from the structure, you're obviously going to take it off the top of the stack. Right, if you have a stack of pancakes, which pancake is the next one you're going to eat? It's not going to be the bottom one. It's clearly going to be the top one. So a stack is basically a structure for data where when you add things to the data structure, you put it on top of the previous things. And when you're going to remove from the data structure, you're going to take off the top of the stack. So let's walk through this example a little bit more. Here we have our stack completely empty and some data. Now, nothing is on the stack right now. So if we were to push the number 1 onto the stack, it would go to the top of the stack. Remember, every time we insert a new value into the stack, it will go to the top of the stack. So if we were to insert the number 2, it would go on top of the value 1. So the top of the stack would then be 2. And then if we were to insert the value 3, it would go on top of the value 2. So the top of the stack would then be 3. And when we're dealing with stacks, we refer to insertion as pushing onto the stack. So the programming language you use, you're going to be using a push method to push values onto the stack. And stacks are awesome because pushing to the top of the stack is actually constant time operation. Now, popping off of the stack is going to remove the top value from the stack. Removing values from a stack always happens at the top. So when you push a new value to the top of the stack, and when you pop a value off the top of the stack. These are constant time operations, and that's why stacks are used in very specific cases. Another method we should be aware of is the peek method, sometimes referred to as the top method, where you just check what is on the top of the stack. Unlike the stack.pop method, this does not remove the value from the stack. So the difference is stack.pop will remove the top of the stack, and then you'll have access to that value, whereas stack.peek or stack.top will just check what is at the top of the stack, and you can just see that and it will stay there. So for example, if we have this stack with the values 1, 2, where 2 is at the top of the stack, and we called our stack.peek method, that would just give us access to the value 2. And then let's say later on we added more values, so now we have 1 through 5. If 5 is at the top of the stack and then we call stack.peek, we're going to get access to the value 5. So everything we just looked at is in constant time, so that's pretty good. And there's a whole bunch of particular scenarios where we'd want to use a stack. However, the one thing that does kind of suck is if we have a bunch of values on the stack and we want to get access to, let's say, the bottom of the stack, well, then we're going to have to pop all of those values on top of the bottom of the stack off. So in this example, if we have the values 1 through 5, but we want to get to the value 1, we would have to do some kind of loop where we just keep popping off of the stack until we get access to that value 1. So unfortunately, that's going to be a linear time operation. Did you know that British people use the word queues to talk about lines? Lines like the things you stand in to wait for something, like at an amusement park. And that's exactly what it is in programming. Unlike a stack, which is a last in, first out data structure, a queue is a first in, first out data structure. And it's pretty obvious why. I mean, if you're getting into a line to get on a ride at an amusement park, the first person in line is the first person out of the line and the first person to ride the ride. So in programming, we're going to have a queue and data. And when we add data into the queue, the first piece of data into the queue will also be the first piece of data that comes out of the queue. If you ever get stuck, just think about the British word queue meaning line, and you'll know what a queue is. Now, the method names could vary depending on the programming language you're using, but when we refer to enqueuing or adding onto the queue, we're talking about inserting onto the end of the queue, so the back of the queue. When we talk about dequeuing or removing from the queue, we will remove from the front of the queue. And then just like a stack, we'll have a peek method, which will allow us to access the value at the front of the queue. So let's look at this example where we have our queue and some data. The data is just the numbers 1 through 5. So if we were to enqueue or add the number 1 to our queue, it would be inserted at the end of the queue. But the queue is empty right now, so it'd just be the only value in the queue. If we were to then enqueue the number 2, that would be added to the end of the queue. And in this case, we already have a value 1 in the queue. So it'd go after 1 in the queue. So now our queue has 1 at the front of the queue and 2 at the end of the queue. If we were to enqueue or add the number 3, then that's going to go to the end of the queue. So that's going to go after 1 and 2. So when you enqueue or insert values into your queue, it's always going to the end of the queue. Now, if we were to dequeue from the queue or remove a value from the queue, well, that's going to be removed from the front of the queue. And we're not going to be passing any specific value into this method because it doesn't take parameters. It just removes a value from the front of the queue. It's similar to how you pop off a stack. However, stacks pop off the most recent added value. Queues remove the least recent added value. So in this case, if we were to dequeue, it's going to remove 1 from the front of the queue because that was the least recently added value. So just so we fully understand, let's just continue with the rest of this example. So after we remove 1, our queue has 2 at the front and 3 at the end. So if we were to then enqueue the number 4, that would go to the end of the queue. And then if afterwards we were to dequeue or remove a value from the queue, it wouldn't remove the value 4, which seems kind of intuitive in your head, but it actually removes from the front of the queue. We just have to remember, first thing in, first thing out. Out of all the values that are currently in the queue, 2 is the first that was added, so it's going to be the first thing out. So I think we get the concept of enqueue and dequeue now. So let's just talk about the last one, peak. So right now we just have 3 and 4 in the queue. And if we were to call peak, 3 is at the front of the queue. Peak is going to give us access to the value at the front of the queue. So that would give us access to the value 3. And really that's all we pretty much have to know about queues. Queues can be implemented in a bunch of different ways. You should look up how to use a queue in your programming language of choice. Now, a lot of you might be wondering, what is a tree? Well, I'm here to explain. In botany, a tree is a perennial plant with an elongated stem, or trunk, usually supporting branches and leaves. In some usages, the definition of a tree might be a little bit narrower, including only wood plants with secondary growth, plants that are usable as lumber or plants above a specified height. Oh wait, you wanted a programming tree? Alright, I guess I could tell you about those too. So a tree is a very popular data structure. We can kind of think about it more like how we think about linked lists, where we're going to have these separate nodes that point to each other. There's different kinds of trees with unique properties. The 3 trees we're going to focus on in this video are a general tree, a binary tree, and a binary search tree. So first, let's just talk about a general tree. The first node of every tree, meaning the very top node, is referred to as the root node. In a general tree, a node can have any number of children nodes. So it could have no children nodes or a bunch of them. Now in programming, trees have levels and heights. The root node is at level 0, its children nodes are at level 1, their children are at level 2, and so on. Until you get to the very last level of the tree, or the bottom of the tree, where those nodes are referred to as leaf nodes. And the height of the tree is just the number of levels. So if there's 4 levels in a tree, then the height would be 4. The next tree we're going to look at is a binary tree. Now unlike a general tree where each node can have any number of children, in a binary tree, each tree node can only have up to 2 children nodes. These children nodes are referred to as the left child and the right child. So if we were to visualize a binary tree node, it would look like this, where each node has a value and it could have up to 2 children. So it could have 0, 1, or 2 children nodes. And then there's a binary search tree. This is a special binary tree where all left subtree nodes will be less in value than the root node, and all right subtree nodes will be greater in value than the root node. Let's look at this example. So here we have our root node with a value of 10. So in a binary search tree, that means the left child of this node will be less in value. And all of the children of that node will also be less in value. So as we see, the left child has a value of 5, which is less than 10. And then if we looked at 5 as the root node, you could see the left child of that node is less in value, but the right child is actually greater in value because 7 is greater than 5. However, 7 and all right children of the node 5 will still remain less in value of the node with the value 10. And then if we were to look at the right side of our root node, all of those nodes are going to have a greater value than the node with the value of 10. So if we look to the right, we see 13, which is greater than 10. The left of that is 11, which is less than 13. And the right of that is 18, which is greater than 13. So that's how a binary search tree works, and it's organized in an order, as you can see. And this allows us to have efficient time complexity on some of these tree operations. All right, so for the pre-order, in-order, and post-order traversals, it's just the order that we traverse the root. So in pre-order, the root comes first. And then left and right are always in the same order where left comes before right. So we're just going to traverse the root node, then the left node, then the right node. Now you might be thinking we traversed the node with the value of 13 next. However, the node with the value 5 that we traversed is a root node in itself, so we continue down that recursive path. So since 5 is the root and we've already seen that, then we would go left, and that would be the node with the value of 3. And then when we're at 3 would be the root. However, it doesn't have any children nodes, so left and right don't exist. So we'd return to our previous recursive call with the root node 5. We already visited the left, so then we'd go right. That would be the node with the value of 7. Once again, there's no children nodes, so we'd return to the previous recursive call, which would be 5. And then we'd return from that recursive call, because the left, right, and root were all visited, to the original recursive call, and we would go down the right side. So that'd be the node with the value of 13. And that would be a root itself. So then we go left. That would be the node with the value of 11. There's no children nodes, returns to 13. Then we visited the left already. So we'd go to the node with the value of 18. No children. We'd return. Then we'd return to the original recursive call. And we would have completely traversed the entire tree using a pre-order traversal. So this is what the code would look like in Java. You could see the function pre-order at the bottom. This is the pre-order traversal. We would pass in the root of the tree. That's how tree problems work. You get the root, so the very top node of the tree, and if the root is null, we're just going to return because there's nothing to traverse. And then as we recurse, that's what we're going to do too. If the root is null, there's nothing to print, there's nothing to traverse, so you just return. That's usually a base case for tree problems, so just keep that in mind. And then as we visit nodes, we'll just print their value, right? Because as we know in a binary tree, the structure of the node is it has a value. It could have up to 2 children. It could have a left node, a right node. It could have no children nodes. So we're going to traverse the tree and print the value of each node as we traverse, but we're doing it in a specific order. And when you look at the code, it's pretty easy to remember these pre-order, in-order, and post-order traversals, because if you look at lines 16, 17, and 18, I mean, it's pretty straightforward. You print the root, you go left, then you go right. And that is the order of pre-order: root, left, right. So we're just looking at each root node, then we go left, then we go right, and the recursion just takes care of it all. So if you're having a tough time understanding this, it might be because you're not that solid with recursion. So maybe check into recursion a little bit more before we try and... All right, in-order traversal. If you remember, pre-order, in-order, and post-order traversals, this is the order we traverse the root. So pre-order root is first, in-order second, post-order it comes last. And then we always traverse the left node before the right node in any of these orders. So in order, we're going to traverse the left node, then the root node, then the right node. All right, so we look at the root node first with the value of 10. Now we wouldn't traverse this because it's left, root, right. So we'd go down the left path. That would be the node with the value of 5. However, that's a root in itself. So we wouldn't traverse that yet because it's left, root, right. So we'd go down the left path even further. That'd be the node with the value of 3. That would be a root in itself. So we'd look down the left path even further. However, it does not have a left child. So in that case, there's nothing to traverse on the left side. So then we would traverse the node with the value of 3. And that would be the root. Then we'd traverse its right node. However, there is none, so that's fine. And it would return back to the node with a value of 5. That node would then be traversed because we already looked down the left side and it's left, root, right. So after 3 and 5 are traversed, we would then go down the right side because it's left, root, right. And we would traverse the node with the value of 7. After that, we'd return back to our first function call with the node with the value of 10 as the root. The left side has been completely traversed now, so we can traverse the node with the value of 10. Remember, left, root, right. We just have to think about these things recursively. Now we can go down the right side. We'd go down the right. However, that's going to be a root node itself, so we have to go down the left again. So instead of traversing the node with the value of 13, we would go to the node with the value of 11. It doesn't have any children nodes, so we would traverse that node. That would have been the left side. Then we go root, which is the node with the value of 13. We traverse that, and then we can go right, node with the value of 18. Doesn't have any children. Traverse that, and that is the entire in-order traversal of this binary tree. All right, so let's look at how similar the in-order code will be to the pre-order and post-order traversals. So this is the pre-order traversal. You can see that you visit the root, then the left, then the right. So it's kind of just the order that you're printing the root node in. So basically we could just copy this function. It's going to be so similar. That's similar. We could just change it to in order. And then the only thing that's off is the order, right? Because pre-order, the root comes first. You can see root, left, right. That's pre-order. In order is left, root, right. So since it's left, root, right, we just have to move left above the printing line. So let's get rid of this comment. So you can now see that we are going to recursively call all the way on the left side over and over and over again until we get to the leaf where the root is null. That will hit that condition, return, and then we'll be at a root node. It will print that, and then we'll check right. So this is the function, as simple as that, left, root, right. In pre-order, it's root, left, right. And then in the next video, we're going to look at post-order, which is left, right, root. Remember that left and right are always in the same order. Where left comes before right, it's all just about the order we traverse. All right, now we do the post-order traversal, and I've said this a million times, but pre-order, in order, and post-order refer to the order the root is traversed. So in our binary tree here, if we were going to perform a post-order traversal, we would traverse the left, then the right, then the root. So if our root is the node with the value of 10, then we cannot traverse that until the end, so we have to go left. The node with the value of 5 would be a root, we'd go left again. The node with a value of 3 would be a root, we'd go left, there would be nothing, then we'd go right, because it's a left, right, root, there would be nothing, so then we'd traverse the root, which would be the node with a value of 3. That would return to our call with the node with the value of 5, we would have traversed the left, so now we go right, then root. So right would be the node with the value of 7, we'd go left, right, there would be nothing, then we'd traverse the root, which would be 7, that would return to the node with the value of 5. Now we've traversed the left, which is 3, the right, which is 7, and now it's time we can finally traverse the node with the value of 5. That would return to our original function call, node with the value of 10, and we now traverse the left side. Now we have to go to the right side. The right side is the node with the value of 13. That's also a root, so we look to the left. The node with the value of 11 is also a root, so we go left, right, there's nothing, so we can traverse the node with the value of 11. Then return to the node with the value of 13. We looked at the left side. Now let's look at the right side. We look at 18. That returns to 13. We can finally traverse that now because the left and right were already traversed. And then we return to our original function call. Both the left and the right side have now been fully traversed, and we can traverse our root. And last but not least, let's look at the post-order traversal, which is going to be almost exactly the same as pre-order and in order. The only difference, like we've gone over already, is it's going to be left node, then right node, then root node. Remember, it's left always comes before right. It's literally just about the order we traverse the root. So in pre-order, root is traversed first. In order, root is traversed second. Post-order, root is traversed last. You might as well just memorize this, and you should just memorize this. So we could just copy this function. You guys already know this is just going to be the same exact thing. Recursive, post-order, and then we'll just change in order to post-order, and then we take the root in post-order. Where do you think it goes, guys? It goes at the end, because it's post-order. Post means end. So left, right, root. We traverse all the way down the left side, then the right. The best way to explain binary search is when we're talking about using a phone book. And yeah, I know nobody uses phone books anymore, but I would hope you know what it is. Anyways, if you don't know what it is, it's just a giant book with people's names and phone numbers. So if you're going to try and look me up in a phone book, how would you do that? Well, my name is Nick, so would you start at page 1 and then flip page by page until you get to the ends? Well, no, because we know my name starts with an N, and N is halfway through the alphabet, so we just open the book up halfway and go from there. And that is the exact concept of binary search. Basically, we don't need to traverse an array element by element if we know the array is sorted. Just like we don't need to look through a phone book page by page if we know it's alphabetically sorted. Now, in any array, if we're looking for a particular value, we know we could just loop through the array until we find it. And in an example like this, where we're looking for the number 9 in a 10 element array, well, that's not a big deal. But what happens when we're dealing with 10 million values instead of just 10? And we're looking for the number 9,999,999. Well, it's going to take a long time to get to that value. And the truth is, in the real world, we're going to be working with data sets where we don't even know what the data is. But if we know the data is sorted and we need to perform a search, then binary search is the way to go. So let's look at a binary search. So let's say we're given an array and we know it's sorted. So for example, we have this array with 10 values, 1 through 10. And let's say we're looking for the number 9. Now, obviously, we could just loop through the array element by element to get to the number 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We would have some kind of condition like, hey, is the current value we're looking at equal to our target? If so, then we found it. However, when we know our array is sorted, this is inefficient. because like I said, if we have an extremely large data set and we're looking for something at the end, it's going to take forever to get there. So overall, in the grand scheme of things, what we're going to want to use is a binary search, which has a logarithmic time complexity, which is better than the linear algorithm of just going element by element. We know from the time complexity videos that our crap solution here is going to be linear time to search for the value, because as the data set grows, so do the operations in a proportionate manner, right? In a linear manner, because, you know, one operation per value, you know, 10 values, 10 operations, 100 values, 100 operations, if you're going element by element. Binary search is going to give us logarithmic time complexity here, which is pretty freaking good, because since we know it's sorted, we can eliminate half of the search space with each operation. So that's going to be logarithmic operations in proportionate to the size of the data. Very, very good. So let's talk about how it works. So basically we're going to have our target, we're going to have our array, and we're going to just look at the middle of the array over and over. So in this case, we're going to look at the middle and we find a 5. And now we're going to compare our target to the middle. And since the array is sorted, if the target is greater than the middle of the array, well, that means it's got to be on the right side. And if it's less than the middle of the array, that means it's got to be on the left side because it's sorted. So the smaller things will be on the left and the bigger things will be on the right. So when we compare target to 5, it is greater because 9 is greater than 5, guys. So that means it's got to be on the right side since it's greater and the array is sorted. So now we know it's not on the left and it's not the middle. So we don't even have to be concerned with any of this stuff anymore. We just act like it doesn't even exist. And now the only part we're going to search is this part. So that was just one operation right there. We searched, we knew it was on the right, and now we're going in for operation 2. Okay, we're looking at this 8. It is on the right side because it's greater. It's not on the left, and it's not the 8. So now we don't have to look at this anymore. That's 2 operations in, and we've eliminated a ton of search space, and we're just down to 2 elements now. And we look at the middle. There's only 2 values, so we just look at 9. Oh, we found it. We found that 9 in 3 operations, compared to if we were doing a linear search, that would have taken 9 to get there. So how incredible is that? Okay, so this is what the code would look like for binary search. So let's say we have this function and we take in an array that we know is sorted and a target value that we're looking for. And we want to return the index that the target is at in the array. So like if the target was 9 and we were given this array with 10 values and we would want to return the index of 9, then we would return the number 8 because it's at index 8. This is exactly like what I just explained. We're literally just going to look at the middle of the array and eliminate half the search space each time, and then look at the middle again and the middle again till we find the value. All right, so the first thing we have here is just to check to make sure there's values in the array. It's an edge case check. You know, we don't really need to worry about this right now, but you should always just check that you're actually given some data to work with. Otherwise, you can get errors when you run your code. So let's just not even worry about that for now yet. Now, the left and right variables we are going to use for our search space. So it starts out with index 0 to the last index of the array. This is the first search space we're working with, so the entire array. And basically, we're just going to loop until we have no search space left to search for. So the main loop will just be while left is less than or equal to right. Okay, so this line calculates the middle index of our search space, and it looks a little bit complicated, but this is just to avoid integer overflow. It's really the middle of left and right, but yeah, like integers can overflow in programming languages, so I write it like this just to handle that case so we don't get any errors. Now we have the index of the middle value, and we want to do those 3 checks. Hey, is our middle value the target itself? Because if so, we found it. If it's not, well, then we should check, is it greater than the middle or is it less than the middle? So we know which side to search on. So we'll say, okay, is it equal to the target? If it's equal, we return the index. We're totally good. Otherwise, okay, let's see if it's less. So if the midpoint is greater, if the middle element's greater than the target, then that means it's less. And we will move our right boundary to the index before the middle. And that's because, okay, we got our left boundary here, our right boundary here. That means we're searching the whole thing. So if our right boundary is over here, and we know that the target's going to be on the left side when we compare, that means we're going to say, okay, let's move our right from over here to right here. So we can just search this side, right? Now, in this case, the target's greater than the middle element. So it's actually going to hit the else, and it'll hit the else because it's not equal to the middle. It's not less than the middle. So it's greater than the middle. So that's the only other option left. So we take our left boundary, which is at the beginning, right? Because we're looking at the whole thing, and we move that up to the index after the middle. So we could search this side. So after that, our left will be moved over, and boom, now we have this left to search, and it will keep going in our loop. And we'll keep looking. We'll look at 8 and we'll say, hey, it's greater than 8. So it's going to hit this condition again. The left boundary will move up again to the 9. And then we'll finally hit the 9. We'll find the index. We'll return. Boom. That is binary. In this video, we're going to cover a slow sorting algorithm called selection sort. So if you're going to be needing to sort a lot of data, this is probably not the algorithm you're going to want to use. But let's learn it anyway, because we always have to learn useless stuff in coding. A lot of the websites and videos online are actually confusing for this, but it's super easy. In selection sort, you just find the minimum and then move it to the front. Like basically you just go through the array, find the minimum element, move it to the front. Now, obviously, when you find the first minimum and you put it to the front, the next minimum you find after that has to go after it, obviously, because it wasn't the minimum. So basically, we're just going to have an index that keeps track of that. So just like the next spot for the next minimum. And once that index gets to the end of the entire array will be sorted. So let's finish the rest of this example. So the next minimum value we found is 4. And the array is sorted until 1. So we place it after 1. So now the array is sorted up to 4, and the next minimum value will go after that. So we look for the next minimum value, it's 5, then we place that after 4. Then we look for the next minimum at 7, and we place that after 5. Now our array is sorted up to 7. The next minimum is 9. That goes after 7. The array is now sorted up to 9. And then the last minimum and the last element left is just 11, and obviously that goes after 9. Boom, the array is completely sorted. Okay, for the pseudocode, we're going to have nested loops that loop through the entire array. The outer loop is going to keep track of where we're sorted until, and the inner loop is just going to go and find that minimum value. So at each iteration of the outer loop, we have an entire loop through the array that finds the next minimum value, and then once we found the minimum value, we swap it with the next available spot after the sorted portion. So the time complexity of the sorting algorithm is O of n squared because we're looping through every element of the array for each element of the array. So this is a lot slower than the better sorting algorithms like merge sort and quick sort. So here's what the actual code would look like in Python. So the outer loop is like the little green underline in the example I went through, where we're going to swap the minimum value with that value. So everything up to right before the ith index is going to be sorted. Now we'll initialize a minimum value in the unsorted portion, and then we'll go through the rest of the array from the next element all the way to the end of the array and find the minimum value, which is, if the current value is less than the minimum value, you update the minimum value. And then after this loop, we would have found the minimum value in all of the unsorted elements, and we could swap it with the next available spot right after all of the other sorted values. You could also implement some kind of swap method for this. But yeah, that's pretty much it, guys. I might even be over-explaining this a little bit. Just take it from what I said at the beginning. You find the minimums, you put them to the front, right? Just don't keep putting the minimum before the other ones you found, right? The minimums have to be in order as well. So find a minimum, put it to the next available spot, next available spot. If you're learning data structures and algorithms specifically to land a job, I do need to inform you there's a little bit more to it than that. The first thing you actually need to do is land an interview. People actually struggle with this, and nobody ever talks about how this is a skill. Now, the standard way to get interviews is just to apply to jobs that you're interested in. But I used to do that in the past, and sometimes I wouldn't hear back from that many companies. So over the past few years, I've learned to take an extreme or very unconventional approach to applying to jobs. Now, I didn't learn this from anyone else. I made this up on my own, and it works pretty well. When I tell other people about this, they think it's excessive or spam-like or just not a professional way to apply to jobs, but it works for me. I've interviewed at hundreds of companies, from startups to top companies, and anytime now that I'm looking for a new job or opportunity, my inbox is going to be full of hundreds of messages within 2 days. So I guess I'm going to share my secret with you guys. So the secret is I apply to thousands of jobs. Now, people don't take me seriously when I say this, but literally, if I look up my applied count on LinkedIn, it will be over 1,000 right now. So here I am on LinkedIn on my display cam. If we click on jobs and we click on my jobs, you can see that the number here is 1,860. LinkedIn is what I use to apply to a lot of the medium-sized or larger tech companies. The other platform I use to apply to mainly startups to medium-sized companies is AngelList. And with AngelList, I literally apply until I hit the limit. Yes, they have a limit on how many jobs you can apply to. So now you might be thinking, well, that's crazy. How long does that take? How do you apply to thousands of jobs? And the truth is, it doesn't take that long. I only apply to jobs that let me apply by clicking 2 buttons. Now let me show you what I mean by that. So here I am on LinkedIn in the job search area. So you look up any job that you want to apply to. So I just searched up software engineer, and now we could see apply easily. And basically what happens when you click this button, you'll hit the button apply, a pop-up will open, it will have your resume, your phone, and your email auto filled in, and then all you need to do is hit submit application, and that is it. Your application is submitted. So I go through and I find any job listing that says apply easily. It's this little thing right here. It says apply easily. And I just sit for 8 hours straight on a weekend or whatever when you have some free time. And you can apply to hundreds, if not 1,000 jobs in one stretch, one long sitting. You just look for these easy apply jobs, you go to it, you hit apply now, pop up, submit application. If it doesn't have an easy apply button, I skip for now, because yes, those applications take much longer. They could take 5 minutes, 10 minutes, 15 minutes to fill out all of the information. But a lot of good and reputable companies do have the easy apply. So anything where you really want to work at a specific company, you could hold those off until the end. And if you go over to AngelList, this is a platform to apply to mainly startups and medium-sized companies, you'll notice that they have easy apply. You hit the apply button and then you hit send application, and that's all you have to do. So you just search software engineer and you just spam these for 8 hours straight. You could dedicate one weekend to applying to jobs and apply to over 1,000 jobs easily. And if you're unfamiliar with these platforms, basically what you do is you fill out your profile beforehand with all of your experience and skills, much like a resume. And that way, all you have to do is hit 2 buttons from then on to apply, because they'll have all your information already. So it's my suggestion for you guys who have a tough time of even landing interviews to follow my strategy, even though it seems kind of crazy. If you're worried about your reputation and spamming and coming off weird, just remember that these recruiters will forget about you in a few days. They look at your resume and they'll forget almost immediately. A lot of these companies are probably going to actually treat you more like a number, so don't be afraid to play the numbers game with them as well. Apply to thousands of jobs. There's no way you won't hear back. There's no way you won't get interviews. There's essentially an infinite number of listings out there. So if you're not hearing back, just keep applying. This is my way of doing things. I'm not saying it's right, and I completely made it up, but it gets me pretty great results. So feel free to try it out. Now, in my opinion, I think people overthink their resumes a little bit too much. So I'm just going to give you the straightforward answer of what you should do. Because honestly, social media and social presence matters almost just as much at this point. So if you don't know anything about resumes, I would imagine that you've just written your resume in a Word document or a Pages file or something like that. And you styled and formatted it yourself, and you just put what you thought was good, your work experience, your name, some information about yourself. Well, I can't say this for sure, but it probably isn't too good, because that was the first thing I did when I made my first resume. When I was trying to get my first internship, I just looked up a resume online and then tried to copy it in a Word file. And only a year and a half later, I realized that it was a terrible resume. And industry standard for resumes, I didn't know this before, but it's pretty commonly known, how you should make your resume. And as far as programmers, software engineers, data scientists, etc., if you go around and look at everybody's resume, like look at all your friends' resumes and look at your resume and compare, a lot of people are going to have the same resume. Or in other words, they're going to be using the same resume template. And that's because you should be using a resume template. So where should you get the resume template? Well, you can make a free account on Overleaf. I have no association with them at all. I learned this in a research fellowship program I was in, but also I've done resume reviews. I've reviewed hundreds of resumes. I've looked at hundreds of resumes, and I notice everybody's using the same kinds of resumes. Everybody has the same resumes. I've had the same resume as a bunch of my friends just by coincidence when I share them my resume. We all get it from the same templates. So if you go to overleaf.com, I'm going to link this in the description. You can make a free account. You just sign up with Google and you go to the templates section. I will also link this, and there's going to be a ton of templates you could choose from, and basically all of these are going to be perfect. So you're just going to click on one of the templates you like. You're going to click open as template, and you're going to edit the placeholder text that they have there, because it's just going to be random information, but it's going to be set up in a nice templated way. So you'll just edit that and add your information, and that's literally all you have to do. All of these templates that are going to be linked in this section are commonly used. I've seen them a million times. Just pick one of these. It's like industry standard stuff. Go in, fill out your information, and that's it. And then as far as the resume, I think people overthink this stuff a little bit too much. You just got to fill it out. Don't leave it too blank. Fill it out somehow. Whatever you got to do to fill it out, do it. If you have to exaggerate a little bit, I'm not going to throw shame at you guys. And, you could put some programming languages you used a few times. You could put some projects you maybe half started and didn't fully finish. Whatever you got to do to fill out the page and make it look impressive, just do it. There's about a 0.1% chance that the person interviewing you is going to grill you on every single detail on your resume. So just, don't flat out lie, but fill it out and make it look nice. Whatever you got to do to make it look somewhat impressive, do that. If you don't have a lot of experience, do some projects. If you don't have a lot of projects, maybe build some. But if you can't build some, I don't know, add online courses, whatever. It's going to make you look good. That's it. You should be good. Get your resume, print it out, boom, that's it. This is a bad day to wear a green shirt. Anyways, I want to cover some pretty important stuff that is not talked about much, like getting the interviewer to like you. Believe it or not, this can matter just as much as your ability to code. And I hate to break anyone's spirit in this course, but the world is not merit-based. I used to believe it was too. You're told growing up, get good grades, go to school, work hard, and you will succeed. And maybe this was the case at one point. But if you really stop and look around you, you'll notice the world isn't merit-based. People can become successful just from a draw of the cards, a stroke of luck. Some people get successful through connections. They don't even do anything. Or they buy a crypto coin, or they dance on TikTok. They were just born attractive, and now they're successful. But this isn't about that. This is just about getting the interviewer to like you, because that can make or break an interview. And just to give you an anecdote out of one interview out of hundreds I've done, one time I was interviewing at a FANG company, and you would think they'd have a strict process they have to follow. However, during my interview, I was given a really difficult problem, a tree map problem. I forget, it was something to do with maps, and it was very difficult. However, before the interview started, we were joking around, me and the interviewer, and we were from the same hometown by coincidence and went to the same high school. Now, we didn't go at the same time, but that connection right there, that we went to the same high school, he passed me based on that. I was bombing the interview, and he said, I have to go get lunch right now. I'm just going to pass you through the next round. He literally said that. Another time I was interviewing at a different FANG company, probably the most famous one. And I was in the phone interview process where you just get asked a question and they make sure you're qualified to move on. I was just doing the interview because a recruiter reached out to me. I wasn't really interested in working there at the time. So I told the interviewer, hey, I didn't study. I don't know this problem. He said, well, try it out anyway. I struggled through it. I kind of got a half-assed answer. And he passed me anyway, because he said that's not what really matters. Point being said, you can pass an interview just by having the person you're interviewing with like you. This is not going to be the case every time. There are a lot of very serious interviewers that take the process very seriously, and it is merit-based. But sometimes you're going to get a relaxed person who's very nonchalant, and they will be lenient with you if they like you. So just a couple tips right now for getting the interviewer to like you. First, I would say try to identify the energy of the interviewer before it starts. You can usually tell if someone's taking it very seriously or not. The friendlier, warmer people that maybe laugh or make jokes, those people are going to probably be more lenient with you, and you're going to want to match that energy. You're going to want to also be relaxed and try and connect to them. Whereas the very serious people who are right down to business and don't want to hear jokes or any of that, you should also match their energy and become very serious, take it very seriously. You kind of just want to match the ideals of the interviewer so that they like you. Before the interview starts, I always like to ask a question to either try to find something to connect with the interviewer on or to make them like me by showing interest in either the job at hand to show that I'm either passionate about it or to show that I'm interested in them because people like attention. Those are my main beginning tips. Now, towards the end, I do think you should ask questions at the end. Try and come up with some unique, cool questions to ask and ask about the job. Try and make it clear that you are passionate about getting this job so that they know you care about it. Because then even if you did poorly in the interview, they might feel bad and say, oh, this guy is so passionate. This person's so passionate about getting this job. You know what? We're going to let him slide. So show that you really want the job at the end by asking questions. A few other important things are don't try to act smarter than the interviewer. If the interviewer says something wrong, politely correct them or don't even correct them at all if not necessary. Like, do not try and act smarter. I did that a while ago and they just won't like you and they could fail you because of that. And then here's the last one. Sometimes you're going to get an interview question where you don't know it. You're going to bomb. Nobody knows every single question. You might get a question and you just, even if you struggle through it for 30 minutes straight, you're going to fail. You just know looking at it, hey, I'm going to fail this. In that case, I recommend, working at it a little, but then make an excuse. Say something that will at least make it look like you're not an idiot. Oh, I was up all last night studying, or I was up all last night working on this and I'm super tired. I, for some reason, couldn't sleep and now I can't remember. Or you could say something like, oh my gosh, I've done this problem before and I somehow, I'm having a brain fart. I just can't think for some reason. Some kind of excuse I would recommend going with if you know for a fact you're not going to solve the problem and you're going to look like an idiot just sitting there. This is better than looking like an idiot, having an excuse, I think, because then maybe they'll be more likely to give you hints or feel bad or, they just won't think you're dumb. So those are all of my go-to communication tactics, trying to get someone to like you. Find commonality between you guys. That's what relationships are built off. Friendships are built off commonalities, common interests. So if you could do that, that's really going to help you out. And getting the person to like you can help you out more than you know.